Springfield Technical Community College in Springfield, Massachusetts offers the only degree program in optics and photonics technology in New England. Optics and photonics is the practical use of lasers, electronics, and optics, and it impacts almost every aspect of our lives. With nearly 100% job placement and starting salaries of $40,000 to $60,000 a year, what are you waiting for? Call our admissions department today at 413-755-3333 or visit www.stcc.edu/laser.
Hey Blaine, you want to see a magic trick? Sure. Can you see the speaker?
Yes.
Okay. We'll hold this. Just keep going. Can you see it now?
Wow, it's almost completely gone. How'd you do that?
Well, you know how light speeds up or slows down when it goes from one material to another, right?
Sure, scientists use something called the index of refraction to measure the speed of light.
Right. When the light goes from the air into the glass, it slows down. It speeds up again when it goes from the glass back into the air.
Yeah, I know. So what?
Well, when light changes speed, some of it is reflected. That's how you see things. The light is reflected off the object.
Oh, so even though the glass is transparent, not all of the light goes through it.
Exactly. The speed of light is about the same in the oil as it is in the glass, so there's no change of speed when it hits it. No change of speed, no reflection.
Oh, so no light from the small beaker is reflected into your eyes. That's why you can't see it.
Exactly. That's what scientists call index matching, because the oil and the glass have the same index of refraction.
I wonder if that has any applications other than magic.
Actually, it's why when you have an ultrasound, the technician puts that gooey gel on your stomach first.
I always thought it was so the transducer could slide over your skin.
Nope, the gel makes it so the sound waves go into your body instead of reflecting off of it.
It's all index matching.
I'm Emily.
And I'm Blaine.
And this was The Disappearing Beaker.
Hi, I'm Catherine.
And I'm Blaine. And today we'll be exploring light spectra.
Can you tell what colors or wavelengths are produced by a light source? Maybe not looking at it with the naked eye, but with the right tool, the colors can be separated and examined.
You see, Isaac Newton, the guy who explained gravity, looked at sunlight through a prism to separate the light into the colors of the rainbow: red, orange, yellow, green, blue, and violet.
They're part of the electromagnetic spectrum, like radio waves, microwaves, and X-rays.
We can see what colors a source is producing.
So why don't we check out a few different light sources and see how the colors differ?
To do this, we'll need to make an instrument called a spectroscope. We'll need a cardboard tube, aluminum foil, and a diffraction grating from the OSA Optics Discovery Kit. If you don't have a diffraction grating, a CD will work just fine. You need the kind of CD that you can record on. If you use a CD, you'll need a pair of scissors to scrape off the label, and you'll need tape to take off the shiny coating. You can cut the clear CD with scissors to fit the end of the tube. First thing we'll need to do is take the cardboard tube and cover it with aluminum foil and secure it with a rubber band.
And then, with a sharp knife, be very careful. Make a small slit in the center of the foil, about 1 centimeter long. You also have to choose a few different light sources to examine. Today, we have an incandescent and fluorescent light bulb.
Look through the grating at any light source in the room. Make sure that the line is vertical and the colors are to either side. If the colors are above or below, turn the diffraction grating.
Okay, so let's take a look at our light sources. Let's start with the incandescent light bulb. Point the slit directly at the light. Look through the diffraction grating. What do you see?
I see a white light filling the slit and colors on either side, with all the colors of the rainbow, red to violet.
Cool. Now let's look at a fluorescent light bulb. What do you see?
Cool. There's still white light filling the slit, But on either side, it's not a full rainbow. There are colors missing.
That's funny. The two bulbs give off a white light, but their light spectra are different. I guess you can't see a light spectrum with the naked eye.
I wonder what a TV screen would look like. Or what colors are given off by a street lamp. Or that exit sign over there.
And we can totally check that out. A spectroscope can look at all sorts of different light sources. But never look into the sun or into a laser, because it could blind you.
Yeah. Spectroscopy, or the study of light, has a lot of interesting applications. The spectrum of light emitted, transmitted, or reflected by an object has a lot of information about what the object is made of.
Like at a crime scene, when a detective is trying to identify an unknown substance, a sample is taken to the lab and spectroscopy is used to figure out what it is.
Spectroscopy is used in everything from diagnosing crop diseases to finding out how much oxygen is dissolved in water to matching paint colors.
It's used by scientists and engineers in biology, environmental science, chemistry, geology, lighting, and more. And it all starts with something like this. I'm Catherine.
And I'm Blaine.
And this was Exploring Light Spectra.
Kathy, can you tell what fruit I have in my hand?
Looks kind of smooth and purple. Is it a grape?
Nope.
Well, I guess it's a little too big for that. Is it a plum?
Nope.
I give up then.
It's a tomato. And before you argue, a tomato is a fruit.
Well, I know that, but why was it purple?
Well, you know the color of an object depends on the light reflected into your eyes, right?
Right, so.
Well, tomatoes reflect mostly red and a little orange, but there's no red or orange in this blue LED light.
And why does it look purple?
Well, the skin of the tomato is really shiny, so it reflects some of the blue light. And since the room isn't really dark, it reflects a little bit of white light. So the combination of the red wavelengths and the blue light makes it look purple.
Oh. Wait, is that why cars look funny under those yellow lights at mall parking lots at night?
Exactly. Different types of lighting give off different wavelengths, and that can make colors look strange. For example, supermarkets need to choose colors of lighting that make their fruits and meat look appealing. Do you remember that department store that had awful lighting?
Yeah, when I got the clothing home, it didn't look the same color.
I guess they should have paid more attention to lighting.
Hey, I wonder what these candies would look like under different color lights. I wonder if we'd be able to tell them apart.
I'm Lydia.
And I'm Kathy.
And this was
What Color Is That?
Everybody has heard of the speed of light, but did you know that light can travel slower depending on what material it's traveling through?
Light can also change direction when it enters a different material. This is called refraction, and it's how lenses, like the ones in eyeglasses, work.
Think about a marching band walking in nice even rows on pavement, but then part of the marching band starts walking through mud. The marchers walking in the mud walk slower than the marchers on the pavement, so the line bends. But that doesn't explain why we have a slab of gelatin here.
Well, to demonstrate, I made an experiment using this gelatin.
Cool!
I used lemon gelatin, so we can see a laser beam travel through it. And it's sugar-free, so it won't make a mess.
Good thinking. So where do we start?
First, cut a rectangle of gelatin using this ruler, so we have nice straight sides.
Okay.
On this paper, I drew two perpendicular lines. Put the rectangle on the paper with one side on one of the lines.
Got it. So where does the laser come in?
We're going to shine the laser along these other lines and mark where the light comes out of the gelatin.
I can see the laser beam in the gelatin, but why can't I see it in the air?
You can't see a laser beam unless there's something to scatter it to your eyes, like dust or smoke or this gelatin. Sorry, but there's really no lightsabers.
Hey, every time the beam bends, so it makes a smaller angle in the gelatin than in the air. I wonder what would happen if we used a different shape. How about if we use a circular cookie cutter and make overlapping circles so it makes a convex lens?
Then take another rectangle and cut circles out of the sides to make a concave lens.
Let's see what happens with the convex lens.
Wow, the beams meet on the other side of the lens. I guess that's why they call it a converging lens.
How about the concave lens?
Hey, the beams separated this time.
I guess that's why they call that a diverging lens.
I wonder what would happen if we tried to make a fiber optic cable out of gelatin.
Cut a long strip of gelatin and arrange it however you want, and then shine the laser beam through it. What do you think will happen when the laser goes through the gelatin? I'm Emily,
And I'm Blaine.
and this was Exploring Refraction.
Nice shades, Emily. Are they new?
Yep, they're UV blocking and they're polarized.
I get UV blocking, but what is polarized?
Well, you know how light's a wave, right? And its vibrations are perpendicular to the direction it's traveling.
Yeah, so.
Well, natural light's vibrations are random, but polarized light only vibrates in one direction. These pieces of plastic from our OSA Optics Discovery Kit are polarizers, just like the plastic in my sunglasses.
Oh.
See, this material is sort of like a picket fence for light vibrations. If I hold it one way, then the up and down light vibrations come through. If I rotate it 90 degrees, then only the vibrations that are side to side come through. The direction of vibration that gets through is called the transmission axis.
What happens if you look through both polarizers?
If you hold both of them with their transmission axis horizontal, you can see through them. But what happens if you rotate one so that its axis is vertical?
Whoa. Suddenly I can't see it anymore. So one only allows for horizontal polarization, while the other only allows vertical, and nothing gets through. Well, cool, but why do they put these polarizers in sunglasses?
I'll show you. Look down the hall there. You see that shine on the floor? Now look at the shiny spot through one of the polarizers and rotate it in front of your eye.
Wow, the shine comes and goes when I do that. First I can see it, then I can't.
That's because the light reflected off the shiny floor is polarized. If you can see shine, the transmission axis of the polarizer is horizontal. If you can't see the shine, then you're holding the polarizer with its transmission axis vertical.
Cool, so this can help with glare from other surfaces like ice or snow. The polarizers in the sunglasses can keep the glare from my eyes.
Exactly, but the polarizers have to be put in the sunglasses exactly the right way. If the transmission axis is vertical, then it blocks the light.
What else can you see with these?
Well, you can block the glare from the surface of the water, and you can sometimes see what's underneath.
Well, that would be handy for fishermen.
Yep, the blue sky is polarized too. Some insects use the polarization of the sky to navigate. That's why you don't see bumblebees on cloudy days.
Really? We should go outside and check that out.
Yep. I'm Emily.
And I'm Catherine.
And this was Exploring Polarization. Hey Kathy, I've been thinking about that polarized light you were talking about earlier.
Yeah?
Well, I've been doing some reading, and I think if we use the polarizing filters, we can make some art with it.
Really? How?
Well, I got this piece of cellophane from the florist the other day, and I think it might get some interesting results if we look at it through the filter.
Oh, cool. Let's try it.
Okay, so cut the pieces of cellophane in whatever shapes you want, and then using a little bit of clear glue, stick it to a piece of plastic about the same size as the filter. Or you could use packing tape so that way you don't have to use the glue.
We glue the shape directly on the clear plastic square because it could damage the polarizer if we glued it directly on that. Then we wouldn't be able to use it for more experiments.
When your art is complete, make a sandwich. First you use one polarizer on the bottom, and then your layer of plastic with your artwork, and then another polarizing filter on the top. And then, using a window or a light source, you can put it on there, rotate the top one, and see what happens.
Wow, the colors change when you rotate the polarizer.
Cellophane changes the direction of the polarized light. Each wavelength vibrates a different direction, so you see different colors as you rotate the top polarizer.
Well, that makes sense. I bet if we made the cellophane shapes thicker, we'd get different results.
Why don't you try it? I'm Emily,
And I'm Catherine.
and this was
Polarized Light Art.